Intermolecular forces and liquids and solids. Comparing the gas state to the liquid state, gas molecules are widely separated in space, moving at high velocities. They have high kinetic energies. But if a sample of gas is cooled and compressed, the molecules approach each other so that the intermolecular forces overcome kinetic energies. And when intermolecular attractions overcome kinetic energies, liquefaction occurs. So you get a liquid. The liquid state is composed of closely packed particles in constant motion. In the liquid state, the molecules still have kinetic energy, but they also have high intermolecular attractions, keeping them together. We'll look at some terms here dealing with liquids. Molecules below the surface of a liquid are influenced by attractions from all directions, but those on the surface are attracted only towards the interior. So if you're at the surface of the liquid right here, you're pulled toward the center, creating a measurable tension in the surface. This is called surface tension. Surface tension is a measure of the quantity of energy required to increase the surface area of a liquid. There are two types of intermolecular forces. There are cohesive forces, which are intermolecular forces between like molecules. So when one water molecule attracts another water molecule, that would be a cohesive force. And there are adhesive forces, intermolecular forces between unlike molecules, such as the molecules of a liquid and that of an underlying surface. If cohesive forces are stronger than adhesive forces, a liquid drop is maintained. When you just wax your car, for example, the wax repels the liquid, and so the water is maintained in a drop. If you have not waxed your car in a while, the adhesive forces are going to be stronger than the cohesive forces, and the water will run off of the surface. Here's a couple liquids, water and mercury. Notice the difference. Water in a test tube forms a meniscus. That is because the adhesive forces are stronger in water than the cohesive forces. So water is more attracted to the glass than it is itself, whereas mercury forms an inverted meniscus because the cohesive forces are stronger in mercury. Mercury is more attracted to itself than to the glass test tube. Capillary action occurs when one end of a capillary is immersed in a liquid. If adhesive forces exceed cohesive forces, the liquid creeps up the sides of the tube until a balance is reached. Next time you have a liquid, you put a straw in the liquid, whether it's tea or water or whatever, notice the level of the liquid in the straw. It's going to be higher than the level of the liquid outside the straw. This is called capillary action. And it will creep up the sides of that straw until a balance is reached between the adhesive forces and the weight of the liquid. Viscosity is the resistance to flow. Molasses has a high viscosity, very high resistance to flow. Water will flow rather easily, low viscosity. Evaporation or vaporization. Not all molecules have the same kinetic energy, even at the same temperature. Some molecules are going to have low kinetic energy, some are going to have high, most are going to be right there in the middle. So we use the term average kinetic energy. Here's a graph of molecules versus kinetic energy for two different temperatures. What I want you to notice is that at T1, the lower temperature, some molecules have a kinetic energy way over here. Some molecules at T1 have kinetic energy way over here. Most of the molecules at T1 are at the peak of the curve, which is right here, so their kinetic energy somewhere about here. Now at T2, a higher temperature, the average is about right here. But even at the higher temperature, some molecules have a really low kinetic energy, some have really high kinetic energy. Molecules with enough kinetic energy to overcome the attractive forces of the surrounding molecules can escape, can vaporize, if they are on the surface. So in order for evaporation to occur, molecules have to have enough kinetic energy and they have to be on the surface. Know those two qualifiers for evaporation. When you lose high energy molecules, that causes the average kinetic energy of the liquid to fall. So when a liquid evaporates, heat flows into the liquid from the surroundings. We're going to replenish those high energy molecules, and this process will continue until all the liquid evaporates. Now the rate of evaporation will increase with increasing temperature. But evaporation is a liquid left to itself. We are not boiling by definition. We are allowing the liquid to be left to itself. Vapor pressure. When an evaporating liquid is confined in a closed container, the vapor molecules can't escape from the vicinity of the liquid. And so what happens in a closed container, if I just have the substance of interest, some molecules will evaporate. In the course of the random motion, these gas particles, some of them will condense back to the liquid state because there's no place for those particles to go. Vapor pressure is the pressure of this vapor when the equilibrium exists between the condensation and the vaporization. So vapor pressure is the pressure pushing upward as these liquid molecules evaporate. Now we have two rates going on here. We have evaporation, we have condensation. And when evaporation and condensation have the same rate, we call that equilibrium. The vapor pressure, though, like I said, is the pressure that pushes upward as molecules evaporate. Pressure pushing upward as those vapor molecules evaporate. If the temperature increases, the rate of vaporization increases, so the vapor pressure will increase if you increase temperature. Easily vaporized liquids are called volatile liquids. Acetone, gasoline, extremely volatile. They will evaporate quickly. Mercury, non-volatile, will not evaporate. Boiling and boiling point. When you have a liquid that's heated to a sufficiently high temperature under a given applied pressure, vaporization occurs throughout the liquid rather than just the surface. The difference between boiling and evaporation is boiling occurs throughout the liquid, evaporation occurs only on the surface. So when you boil a substance, bubbles are going to rise because it can occur throughout the liquid. The boiling point is the temperature at which the vapor pressure is equal to the applied pressure. So a substance will boil when the vapor pressure, pressure pushing upward, is equal to the applied pressure, or atmospheric pressure in most cases. The normal boiling point is the temperature at which the vapor pressure is 1 atmosphere. If you heat a liquid in a sealed container, the temperature and vapor pressure rise continuously. The liquid does not boil. This is because eventually the surface tension of the liquid will go to 0, and the liquid and the vapor will become indistinguishable from one another. But the liquid will not boil in a sealed container. A couple terms here: critical temperature, critical pressure. Critical temperature, the temperature above which the gaseous form cannot be made to liquefy. For water, critical temperature, 374.4. If I get above that temperature, let's say 374.5, water will remain in the vapor phase, regardless of how much pressure I apply. If I want to turn water into a liquid at the critical temperature, I can by applying 219.5 atmospheres of pressure. So right at 374.4, I can liquefy water if I apply 219.5 atmospheres of pressure, which is called the critical pressure.